And so I at least want to say some incomprehensible things about that, and then we'll have that much done. All right.
On that just point, does it have to be incomprehensible?
Do you know what the Schrodinger equation is?
Yes.
Do you know what the Dirac equation is?
What does no mean?
Well, my point is you're going to have some feeling that you know what the Schrodinger equation is.
Yes.
As soon as we get to the Dirac equation, your eyes are going to get a little bit glazed, right? So now why is that? Well, the answer to me is that you want to ask me about the theory of everything, but you haven't even digested the theory of everything as we've had it since 1928, when Dirac came out with his equation. So for whatever reason, and this isn't a hit on you, you haven't been motivated enough in all the time that you've been on Earth to at least get as far as the Dirac equation. And this was very interesting to me after I gave the talk in Oxford. New scientist who had done kind of a hatchet job on me to begin with sent a reporter to come to the third version of the talk that I gave. And that person had never heard of the Dirac equation. So you have a person who is completely professionally not qualified to ask these questions, wanting to know, well, how does your theory solve new problems? And it's like, well, in the case of the Dirac equation, well, tell me about that. I don't know what that is. So then the point is, okay, I got it. You're not even caught up minimally to where we are now. And that's not a knock on you. Almost nobody is.
Yeah.
But then how does it become my job to digest what has been available for like over 90 years?
Well, to me, the open question is whether what's been available for over 90 years can be, there could be a blueprint of a journey that one takes to understand it, not to be.
I want to do that with you. And I one of the things I think I've been relatively successful at, for example, you know, when you ask other people what gauge theory is, you get these very confusing responses. And my response is much simpler. It's a theory of differentiation, where when you calculate the instantaneous rise over run, you measure the rise not from a flat horizontal, but from a custom endogenous reference level. What do you mean by that? It's like, okay. And then I do this thing with Mount Everest, which is Mount Everest is how high? And then they give the height. I say, above what? Then they say sea level. And I say, which sea is that in Nepal? They're like, oh, I guess there isn't a sea because it's landlocked. It's like, okay, well, what do you mean by sea level? Oh, there's this thing called the geoid I'd never heard of. Oh, that's the reference level. That's a custom reference level that we imported. So all sorts of people have remembered the exact height of Mount Everest without ever knowing what it's a height from. Well, in this case, in gauge theory, there's a hidden reference level where you measure the rise in rise over run to give the slope of a line. What if you have different concepts of where that rise should be measured from that vary within the theory, that are endogenous to the theory? That's what gauge theory is. Okay, we have a video here, right?
Yeah.
Okay. I'm going to use my phone. If I want to measure my hand and its slope, this is my attempt to measure it using standard calculus. In other words, the reference level is apparently flat, and I measure the rise above that phone using my hand, okay? If I want to use gauge theory, it means I can do this, or I can do that, or I can do this, or I can do this, or I could do what I did from the beginning, okay? At some level, that's what gauge theory is. Now, that is now, I've never heard anyone describe it that way. So while the community may say, well, who is this guy and why does he have the right to talk in public? I'm waiting for somebody to jump out of the woodwork and say, you know, Eric's whole shtick about rulers and protractors leading to a derivative. Derivatives are measured as rise over run above a reference level. The reference level is not fit together. Like, I go through this whole shtick in order to make it accessible. Mm-hmm. I've never heard anyone say it. I'm trying to make Prometheus would like to discuss fire with everybody else. All right, I'm going to just say one thing to close out the earlier line, which is what I think we should have continued with. When you take the naturally occurring spinners, the unadorned spinners, the naked spinners, not on this 14-dimensional manifold, but on something very closely tied to it, which I've called the chimeric tangent bundle. That is the object which stands in for the thing that should have had length and angle on it, but just missed, okay? When you take that object and you form spinors on that and you don't adorn them, so you're still in the single origin story, you get very large spinorial objects upstairs on this 14-dimensional world Y14, which is part of the observers. When you pull that information back from Y14 down to X4, it miraculously looks like the adorned spinners, the festooned spinners, the spinners that we play with in ordinary reality. In other words, the 14-dimensional world looks like a 4-dimensional world plus a 10-dimensional complement. So 10 plus 4 equals 14. That 10-dimensional complement, which is called a normal bundle, generates spin properties, internal quantum numbers, that look like the things that give our particles personality, that make, let's say, up quarks and down quarks charged by negative 1/3 or plus 2/3, that kind of stuff, or whether or not, some quarks feel the weak force and other quarks do not. So the X4 generates Y14. Y14 generates something called the chimeric tangent bundle. Chimeric tangent bundle generates unadorned spinners. The unadorned spinners get pulled back from 14 down to 4, where they look like adorned spinners. And we have the right number of them. You thought you needed 3, you only got 2. But then something else that you'd never seen before broke apart on this journey. And it broke into another copy of the thing that you already have 2 copies of. One piece of that thing broke off. So now you have 2 generations plus an imposter 3rd generation, which is, I don't know why we never talk about this possibility in regular physics. And then you've got a bunch of stuff that we haven't seen, which has descriptions. So people always say, does it make any falsifiable predictions? Yes, it does. It says that the matter that you should be seeing next has particular properties that can be read off.
Like
weak isospin, weak hypercharge, like the responsiveness to the strong force. The one I can't tell you is what energy scale it would happen at.
So you can't say if those characteristics can be detected with the current.
But it may be that somebody else can. I'm not a physicist. I'm not a quantum field theorist. I can't. I don't know how you would do that.
The hope for me is that there's some simple explanations for all of it.
Lex, should we have a drink?
You're having fun.
No, I'm trying to have fun with you. You know that.
No, there's a bunch of fun things.
But you're very serious.
To talk about here.
Anyway, that was how I got what I thought you wanted, which is, if you think about the fermions as the artists and the bosons as the brushes and the paint, what I told you is that's how we get the artists.
What are the open questions for you in this? What are the challenges? So you're not done.
Well, there are things that I would like to have in better order. So a lot of people will say, the reason I hesitate on this is I just have a totally different view than the community. So for example, I believe that general relativity began in 1913 with Einstein and Grossman. Now, that was the first of like 4 major papers in this line of thinking. To most physicists, general relativity happened when Einstein produced a divergence-free gradient, which turned out to be the gradient of the so-called Hilbert or Einstein-Hilbert action. And from my perspective, that wasn't true. This is that it began when Einstein said, look, this is about differential geometry, and the final answer is going to look like a curvature tensor on one side and matter and energy on the other side. And that was enough. And then he published a wrong version of it, where it was the Ricci tensor, not the Einstein tensor. Then he corrected the Ricci tensor to make it into the Einstein tensor. Then he corrected that to add a cosmological constant. I can't stand that the community thinks in those terms. There's some things about there's a question about which contraction do I use. There's an Einstein contraction. There's a Ricci contraction. They both go between the same spaces. I'm not sure what I should do. I'm not sure which contraction I should choose. This is called a Shiab operator for ship in a bottle in my stuff.